Good morning to everyone. My name is MAYRA, and today I'm going to talk about Taylor Vortex effect on crystal agglomeration in continuous crystallizer. So, first of all, what is the Taylor fluid motion? The Taylor fluid motion is the fluid that is between two concentric cylinders. In our case, the inner cylinder is rotating, meanwhile the outer cylinder is fixed. So between the gap between the inner and outer cylinder is our working volume. In here we can see how is the velocity profile. So how this fluid motion starts? It starts with Isaac Newton, long time ago. He proposed the first corollary about this movement between two concentric cylinders. After that, Gabriel and Stokes with Navier, they established the basic equation for hydrodynamic conditions. But it was with Max Margulis, Malloch, and Maurice Coutet who formulated this motion with viscosity experiments. They tried to measure the viscosity of different fluids. But it was with Taylor who he determined that the motion that is inside, it was turbulent. These three, Coutet, Malloch, and Margulis, they only study about laminar flow. But Taylor established that inside the turbulent motion has ordered patterns, as we can see in here. He said that even though the flow is turbulent, it's ordered. In here we can see how the regimes are inside the Coutet-Taylor vortex flow. It goes from laminar Coutet flow until turbulent flow. And it depends according to the radius between the Taylor number and the critical Taylor number. The Taylor number depends on the rotation speed and also in the geometry of the system. So why we want to use the Coutet-Taylor crystallizer in the agglomeration reaction? We can use also MSMPR or CSTR crystallizer. But the Coutet-Taylor crystallizer has a periodic fluid motion. Meanwhile, the MSMPR crystallizer has random eddy motions. But this periodic fluid motion gives us some advantage as effective for promoting the interpartial mass transfer. Also a high productivity because it reduces the mean residence time and also has excellent micromixing effects. So these micromixing effects have been used in different areas as a polymerization or precipitation, also in biotechnology applications such as growth of cell cultures, and also it has been used as a particle classification. But in our research group, we are exploring the crystallization of this CT crystallizer. We have done experiments about anti-solvent crystallization, also phase transformation, and continuous drawing out. Now, in my case, I want to explore how it reacts with the agglomeration reaction. In my case, I'm going to synthesize metal hydroxide particles. Metal hydroxide is a cathodic precursor of lithium-ion batteries. So first, how is the agglomeration process? We pump into the crystallizer sodium hydroxide and metal sulfate. Then we create the individual crystals. Then they collide each other, and after that, if the collision between them is strong enough, they have two options, to grow or to breakage. All depends on the shear rate. And after that, if they are strong enough to withstand this shear rate, they can grow and form the agglomerate crystals. So this process is controlled by the rotation speed and also the mean residence time. These are the operational parameters that we are going to use. But in order to synthesize a good metal hydroxide particle, we need to control the uniform size and the morphology. In this case, we want a spherical shape. Why? Because we want to improve the tap density. Because the tap density is one of the most critical factors to determine the electrical capacity of a cathode material. So to do this, we have here our experimental procedure. We are going to pump our solution with 3 pumps. This is the heater to control the temperature inside the crystallizer. This is the inner cylinder, the outer cylinder. At this port, we take our sample that is controlled by the pH. The analysis that we run was FSM, PSA, and tap density. Also, in our result, we want to explore how is the Taylor vortex flow regime. As I mentioned before, the Taylor vortex depends on the rotation speed and the geometry. So in this case, we are going to use 3 different inner cylinders: large, medium, and small. And the geometry, we are going to define it with this factor, the radius ratio between inner and outer cylinder. So here are our results. First, we are going to compare the geometry effect of the Taylor vortex. In here, we can see the transient behavior of our reaction. This is to show you that only with 6 mean residence time, that for 60 minutes, we can get our steady state. That means that it's very quickly when we can start to have good material. After that, we can see that the agglomerate particle size decrease as the rotation speed increase for all cases, but it is stabilized around 6.5 micrometers for the geometry 0.93 and 0.89. Meanwhile, for the geometry 0.96, it stabilized around 4.5 micrometers. Why is this big difference? Because these conditions is in the turbulent regime. Meanwhile, this is for turbulent vortex regime. So we can see a big difference between different regimes and different vortex flow. In here, we can see our agglomerate particles, how the shape and the size distribution change according we increase the rotation speed. As we increase the rotation speed, the particle became spherical and also is narrow size distribution. Now, what about if we compare the 3 geometries? We can see that as the geometry decreases, we can get more spherical particles and also the size distribution is improved. In here, we can see that the size distribution we are going to represent according to the coefficient of variation. So, as we increase the rotation speed, the CV value will decrease. And as we increase the rotation speed, the tap density will increase. And the best tap density and the best CV value is for the small radius rating. So, if we want to explore more about this, let's study the average shear rate. In here, we correlate the rotation speed with the average shear rate. We can see that as the geometry decreases, the shear rate will decrease. So, if we correlate our agglomerate particle size with our average shear rate, according to the equation of Jervis et al., we can get the particle stress coefficient and the particle size exponent. These values, compared with previous studies, is higher. That means that our particle is strong enough to withstand the shear rate that we input into the crystallizer. Also, we correlate the coefficient of variation at the tap density with these 2 equations. We can see that as the geometry decreases, the CV value will decrease, and also as the geometry decreases, the tap density will increase. So we proceed to correlate CV value with tap density, and we can see that all match in one straight line, no matter which geometry we use. So that means if we can control the morphology and the size distribution, we can get a higher tap density. Now, what about the mean residence time? As we increase the mean residence time, our particle size will increase, and also the shape will become spherical. This is because as we increase the time, the flow rate will decrease. If we decrease the flow rate, the supersaturation will be proportional along the CT crystallizer. So this means that this will allow the crystal growth. In here we compare the 3 geometries. As we can see, for the small geometry we can get better particles and also better size distribution. this is reflected also in the CV value and in the tap density. So the morphology changed with the mixing intensity. As we increase the rotation speed and the geometry decreased, the particles became spherical in shape and were narrowly distributed. So we can effectively synthesize metal hydroxide with a spherical shape and narrow size distribution. Also, our highest tap density was 2.5 grams per milliliter, and a narrow size distribution according to the CV value 0.22. It was achieved with this geometry and this rotation speed. So we can say that these conditions are the best for synthesize a high packing density for this material. And also we can see through the correlation between CV and tap density that as the CV value decreases, we can get higher tap density for the metal hydroxide particles. Thank you.